the overall goal really is to model the capability of a system. Okay, it's either flexible or it's opportunistic, and so we call that selfish or unselfish. And the model we are going to present is a Markov chain model. Markov chains have become very popular now in data analysis, essentially since the PageRank algorithm was developed for web browsing in Google. Markov chains have gained a certain amount of a name recognition, but here the Markov chain we are presenting is essentially in the context of project management. Okay, and so what our model will essentially be able to achieve is answer questions for what if analysis. So if the system of systems is interested in knowing how flexible a given system is, okay, or what will be the reaction to a budget presented, or what will be the reaction to a deadline, or will this particular system actually, in what way will this particular system respond to a given call, okay, and so the system of systems is obviously interested in understanding what kind of behavior can be expected from any given system. And so what our Markov chain model will do is it will essentially enable us to give a numerical estimates for the budget, for the performance, for the deadline that the system would respond, that the system would essentially respond with. Okay, so essentially what the second bullet point there is the ability to determine the budget and schedule for any given negotiation model. So from the perspective of the system of systems, okay, how will this particular system respond? And so those kinds of answers are very useful in the negotiation process. So what will be the value of this model we are proposing? The value will be, it will be very useful in testing opportunistic behavior present in industry partners. The industry is full of risk-averse and risk-prone behaviors, and so we want to model that particular aspect of the system's behavior, and also the ability to model very unselfish versus selfish systems. Okay, so selfish systems are essentially that will try to go for the biggest possible budget, whereas selfless systems would work with a smaller budget. Okay. Potential applications, okay, modeling of defense firms competing to obtaining a contract, okay, modeling of the project duration, like I said before, okay, and any kind of change. So if you want to make a change to a system's behavior, can you tune some parameters and get different kind of behavior? So that again is an application, and in the future we want to test this on risk-prone behavior of systems, okay. And also see if we can implement some machine learning algorithms, reinforcement learning algorithms within the framework of systems. Okay, so the semi-cooperative Markov chain model that we proposed is essentially using the notion of project management, which means that when a work is assigned to a given system, by the system of systems, we view that as a project that goes through phases. Okay, so typically any project, it starts, then it goes through a phase in the middle, and then it terminates. So almost any project can be viewed in that framework. And so the work that will be assigned to the system of systems is going to be one that takes a random amount of time. And so so the reason we've used a Markov chain model is it allows us that flexibility. We can have a project that takes a random amount of time, okay, and so that and then we can predict how long, what will be the expected amount of time that a project will take to complete. And also in the process we will be able to estimate the kind of funds needed, by when the project will be completed, the deadline, okay, and what will be the performance that one can expect from the project, and so on. Okay, so the internal phases of this project are going to be essentially the states of a Markov chain. Okay, and so there's essentially three states in the Markov chain: the starting, the middle state, and the completion. And this is going to be an absorbing Markov chain. That means once it enters the completion state, the project is over. Okay, And the willingness to cooperate will essentially be computed using the internal dynamics of the Markov chain model. So the willingness to cooperate is going to depend naturally on the task at hand, okay? What's the kind of load that the system has, how many systems it is interacting with, and so on, okay? And I'll explain that quickly in the next slide, okay? So here are some of the input parameters. So the eta is the selfishness parameter that goes from 0 to 1. Of course, it's an interval, and it can never really be 0, but it can be very close to 0. When it's very close to 0, it means we have a very unselfish system, a system that will require very little money. The budget will be very small. On the other hand, 1 is essentially a system that's very selfish, and it will try and extract as much money as possible from the system of systems, okay? And L and M are the agility parameters. So they model how quickly the system will transition and how quickly it will finish the project, okay? Again, these can be tuned. So both eta and L and M are parameters that can be tuned, and so on basis of that we set up this Markov chain model. It has its transition probabilities. This is the transition probability matrix that you see here, okay? And then analyzing this matrix, we can compute the so-called Q matrix from it, and then via some matrix inversion, and I won't go into the details of that, okay, you can, using standard techniques in Markov chains, you can essentially obtain how long it is that the project will take to complete. And K essentially is the number of systems, the total number of systems. N is the number of systems with which it interacts. Okay, so when you set K to N, you have essentially a system that is interacting with all the other systems, and so that is a system with a very heavy workload, and that's bound to be the slowest possible system, okay? And so using different values of L, N, and setting K to N, we can find an upper bound on the amount of time that the system can take, okay? And then that's tau max, and tau I is the actual amount of time that this specific system will take. And so 1 minus tau I divided by tau max essentially gives us the probability that this system will be willing to cooperate, okay? And so this phi is the willingness to cooperate, okay? And like I said, it's 1 minus tau I divided by tau max. And so it can be 1 or it can be 0, okay? And so when it's 1, it essentially means that it's really under a light load, and if Pi is the performance that's expected from the system, then that is the performance that you will get. So Pi times phi is the actual performance of the system. As phi falls, okay, goes down from 1 to 0, the performance will also degrade, okay, so to speak. And so that's how we compute for any given system the level of performance that you can expect. Regarding deadlines, again, if di is the deadline provided by the system of systems to the system, then the system in turn will actually come up with a deadline which is di divided by phi. Again, if phi is 1, which means the system is very willing to cooperate, it will be precisely the deadline that the system of system offers, but otherwise the deadline, is going to be a later deadline, okay, depending on the value of phi. And then last but not the least, how does the system estimate the budget? Okay, so Fi, which I show here, okay, Fi is the actual funding that is provided to the system, okay, and so if I divide Fi by eta, that gives us my essentially how I would estimate the upper limit on the budget. Again, I won't go into all the details here, but the upper limit on the budget will essentially allow me to compute the rate at which the system of systems can fund projects, and from that, okay, using our scaling parameter, we can estimate what will be the budget that comes from the system, okay. And so we ran this model with a large number of values for eta, beta, L, M, okay, and so we have some of these some of these tests here, and we found that we get very encouraging performance. We get a whole spectrum of behavior from very selfish to very unselfish, from very sluggish to very fast, and also from very high quality performance to very low quality performance by tuning, essentially by tuning some of these parameters. And we have some of the work that we've done here is in these slides, which have been is on this slide, and these are publications. Some of them are conference papers, some of them are journal papers accepted. There's a number of working papers, and the project in general has generated a lot of numerical results and some very encouraging numerical results. Thank you.